Okay, thank you for your introduction. In this talk, I shall review some results of our investigation of the dynamics of charged matter in the vicinity of magnetized black hole. This work was done continuously during recent few years in collaboration with Vladimír Karas, Ondřej Kopáček, and Zdeněk Stuchlík. And it basically concerns the toy model of astrophysical corona residing in the central parts of accreting compact systems. Does it work? Oh yeah, it does. Okay, first let me go through the outline of the talk. In the introduction, I shall provide some astrophysical motivation of our work. Then I give a formal description of this model, and this formal description includes the explicit listing of the electromagnetic vector potential A mu, and then we also quickly review the structures of the magnetic field lines which may arise in given setup, and then also the equations of motions which we integrate numerically to obtain the trajectories will be reviewed quickly. In the second part, I review the dynamics of this particles itself, and it's divided into two subsections. First, we treat the aligned magnetic fields. Then we consider generalized setup of inclined magnetic fields, and we will treat separately of equatorial motion, cross-equatorial, and equatorial motion. Yeah, then I will quickly summarize. So this is introductory figure is the artist's conception of the X-ray binary system GRS 1915, which hosts the Milky Way's heaviest black hole, just something between 10 to 18 solar masses, and the setup is as follows: the companion star is feeding the black hole. The accretion disk is formed, and also the jet emerges from the inner parts of the accretion disk. And in the inner part of the disk, we suppose that the main body of the disk itself is surrounded by the diluted plasma found or residing above and below the main body of the disk, which is denoted as the astrophysical corona. And for this region or for this corona, we provide a simple, like a single particle toy model in this work. There are a few notes on the accretion disk corona and large-scale magnetic fields, which we use as an ingredient of our model. So we state that the accretion disk corona, which consists of this diluted plasma, plays a key role in the formation of observed X-ray spectra of both active galactic nuclei and microquasars. This is a common assumption or common model, and the power law component of this spectra is resulting from the inverse Compton scattering of thermal photons, which are emitted from the inner parts of the accretion disk, and undergoing this Compton scattering, they transform to X-ray band, and thus these electrons therefore should have impact on the observed spectra. Their dynamic properties like resonances or dynamic regimes, if it's regular or chaotic. But this question of observational imprints within our model is yet to be elaborated. So it's just a note at the moment. Also, numerical simulations of GR-MHD demonstrate that this astrophysical corona plays a significant role in, or essential role maybe, in collimation and acceleration of the jet, and it also shows that these simulations that the regions above and below the accretion disk may become dominated by the magnetic pressure, and that large-scale magnetic fields may develop here by dynamo action. And the last note is from the observational point of view, namely the observations of Milky Way's galactic center in a radio band revealed that the presence of ordered large-scale magnetic fields, which I show in this slide. So this is the Milky Way's galactic center at wavelength of 90 centimeters, and the black plot in the center is the very center of our galaxy, and those narrow structures here and here are non-thermal, narrow non-thermal filaments, which trace the ordered magnetic field whose strength may reach 1 milligauss, while the average strength of the interstellar magnetic field is by 2 orders of magnitude lower. It's about 10 microgauss. So this proves that the large-scale magnetic fields are present in the central parts of our galaxy. This snapshot originates from the Very Large Array. So here I formally describe our simple model. We employ the Kerr metric in Boyer-Lindquist coordinates tr theta phi, and we add the vacuum solution of electromagnetic field described by this vector potential a mu, and the field we use is the asymptotically uniform magnetic field into which is this Kerr black hole immersed. It's treated in a test field approximation, so the electromagnetic field doesn't affect the geometry, but the geometry affects the field. First, we consider aligned magnetic field, which means that the asymptotical magnetic field is parallel with the rotation axis of the Kerr black hole. This is described by the Waltz solution from 1974, and then also we consider the asymptotically uniform magnetic field with general orientation of the with respect to the rotation axis, and this solution was given by Bichak in 1985. Here I list the components of vector potential explicitly. So these BZ terms describe this Waltz field, and these BX terms describe the component which is asymptotically perpendicular to the rotation axis. And we also superpose the Kerr-Newman test fields just to have extra freedom or extra parameter in a system. But we will see that the Kerr-Newman test field doesn't affect the dynamics significantly. Well, it affects the charged particles, but it doesn't act as a trigger for chaos, because, as is known, the Kerr-Newman, the system of charged particle in Kerr-Newman spacetime is fully integrable. So also the test field, Kerr-Newman test field, doesn't act as an integrable perturbation. Here I show few figures which are illustrating the structures of magnetic field lines which may arise in given setup. We begin with the aligned field on the very left. It's extremely rotating Kerr black hole with the spin equal m or 1 if it's dimensionless, and in this case the field shows the so-called Meissner effect, and all the field lines are expelled by the horizon of the black hole. It only occurs for extremal spin when the field is asymptotically aligned. It's Waltz test field. However, if we incline the field, the Meissner effect is gone, and those field lines may penetrate the horizon, and we observe that the structures of the field are becoming more and more complex when we are increasing the inclination angle. So it suggests that also the dynamics of charged particles will be more complicated than it was in the simple aligned waltz field. Yet another illustration of the field lines. The upper two figures show compare the case of Schwarzschild black hole, in which case the magnetic field is indifferent or is not affected at all by the gravitation of the source of the Schwarzschild black hole. But once we switch the rotation on to the extremal value of extremely rotating Kerr black hole, we see that the field entangles in a quite complex way. So in this figure, the asymptotical direction of the field is perpendicular to the rotation axis, which is like this. And those three figures compare the same situation, extreme Kerr black hole, in an equatorial plane, because in this case the field is confined to the equatorial plane. If the asymptotical component is purely perpendicular to the rotation axis, then in the equatorial plane there is no component going outside the plane. Well, so this is a complete field. And it just compares the situation for three distinct observers. So in the first one we employ the tetrad of freely falling observers. In the other it's co-rotating Keplerian observer. And the third one is the counter-rotating Keplerian observer. And yeah, it shows some differences. So of course the structure of the field is observer dependent, but the overall picture is similar, I would say, and asymptotically it becomes the field becomes the same for all observers because they like merge into static observer asymptotically. Yeah, and details on these fields, including the boost of the black hole, may be found in these references. We considered also in these papers the translational motion of magnetic of black holes through this magnetic field, which results in even more complicated structures of the field. So I go quickly through the equations of motion. We employ the Hamiltonian formalism, in which the equations of motion look as follows. Instead of proper time, we use Fn parameter lambda as a integration variable, and the relation between this p mu, which is the kinematical form momentum, to the pi mu, which is canonical form momentum, is given by this formula. We note here the q is the specific charge of the particle under consideration, and yeah, that is. And A mu is the vector potential of the electromagnetic field, which was listed, which was given explicitly a few slides ago. We observed that the Hamiltonian is autonomous. It doesn't depend on this proper time or Fn parameter. Therefore, it is one constant of motion. And first, we remind that we recall that the charged particle in a pure Kerr-Newman space-time has or this applies to all axially and stationary symmetric, to all stationary and axially symmetric situations. That there are two obvious constants of motions, namely the energy and the angular momentum, which correspond to cyclic coordinates t and phi, which do not appear in the Hamiltonian. And but what is special for this Kerr-Newman spacetime is that there exists yet another independent integral of motion, namely the Carter's force constant, which was found by Carter in 1968, and therefore the system is completely integrable. And in such a system, we would find no traces of deterministic chaos, because all the trajectories in such a system are bound to a two-dimensional hypersurface in the phase space, and in the Poincare surfaces of section, which reduce the dimensionality by 1, we would find only the one-dimensional curves. In this case, we construct a two-dimensional effective potential, by which we mean that that it captures the simultaneous turning points in r and theta coordinates, and of course it's also a function of other parameters of a given system. And this function, this effective potential, allows us to locate bound orbits, bound of equatorial orbits, by searching for its local minima of this function. But in this case of Kerr-Newman spacetime, it actually appears that there are no stable of equatorial orbits above the horizon of Kerr-Newman black hole. So these orbits are not simply not allowed in this situation. However, if we consider this asymptotically, if we superpose this asymptotically uniform magnetic field given by Wolt's solution, we find that these of equatorial stable orbits are possible, that we can locate of equatorial minima of the effective potential. And we also find that, contrary to the previous case of Kerr-Newman, of pure Kerr-Newman, that the system is non-integrable, which means that there is no fourth integral of motion in analogy with Kerr-Newman case, and therefore in such a system the regular and chaotic orbits generally coexist in the phase space. And as a last point, you know that the general situation of inclined or oblique magnetic fields, that the system now has one more degree of freedom, so it has 3 degrees of freedom. The axiosymmetry is obviously broken, and therefore the pi phi, which used to be an integral of motion, fails to conserve now. And as a consequence, it's not possible to construct the effective potential in this case. So we have no tool to systematically search for bound orbits, for equatorial, circular, or other bound orbits, which is quite unfortunate. And also that the Poincare surfaces of section become tricky, the interpretation, because of the dimensionality of the problem, because the section plane doesn't reduce the dimensionality of the problem enough to allow for the simple interpretation of the Poincare surfaces. And therefore we apply the standard tool maximal Lyapunov exponent chi as a basic indicator of chaos in this case. So this shows the classification of possible topologies of equatorial potential lobes in the ball situation. So this is in the aligned field where we have the effective potential, and it allows us to find the lobes of bound motion. To explain the situation, here are located symmetric of equatorial potential minima, and once the energy increases, this applies to this first type 1A. That there is a saddle point residing in the equatorial plane which separates those of equatorial minima, and once the energy, this is an equipotential line for a given energy of this particle, and once the energy is reached, the particle may freely travel between the regions above and below the equatorial plane, and this is what we denote across equatorial motion. So it's the situation when we have of equatorial potential minima connected by the saddle point in the equatorial plane. And if the energy is further increased, there is another saddle point which lets the particle escape to the horizon, to fall onto the horizon. These bold lines always, in all those figures, denote the horizon of the Kerr black hole. And in type 1b, the situation differs, so in such a way that the lobes of equatorial lobes first open toward the horizon, so there is no phase of cross-equatorial motion. The same is true for the type 1c, where before allowing for the stable or bound cross-equatorial motion, the particle is allowed to escape. And finally, the last type, it again allows for the cross-equatorial motion, but there is no saddle point which would allow for the particles to penetrate the horizon. It rather escapes to infinity once this lobe breaks by increasing the particle energy. So in the following we will be interested only in type 1a and 1d because they have this interesting phase of cross-equatorial motion. Well, this illustration of what type of orbits we are interested in. The gray surface is again the horizon of the Kerr black hole, and in this upper right part of this figure, we see this projection of the orbit of equatorial orbit, which never reaches the equatorial plane. But once the energy of this particle would be increased or is increased, it allows for a cross-equatorial motion, and we will see, or we have found that in the case of this cross-equatorial motion, the regime of motion is typically chaos, deterministic chaos, while in the off equatorial lobes, the particles were, or the trajectories were typically regular. This right panel shows the same trajectory as is shown in this slope, but it's in the stereometric projection to have a clear picture of what's going on. Because actually these two trajectories would interweave with each other. It's plotted in one figure just to save space. Well, so this was the first time of the potential, first type of the potential topology, 1A, which allowed for the cross-equatorial motion, and and this is the other one. Again, just a brief illustration of possible trajectories. We start in off equatorial lobe, and in this case, again, the trajectory appears to be regular, but then the energy is increased, cross-equatorial motion occurs, but here for some while it can stay still regular. But then also the chaos comes into play or emerges if we further increase the energy. This here we employ just another tool to investigate the dynamics of to numerically investigate the nonlinear dynamics, namely the recurrence plots, which also allow to distinguish clearly between regular and chaotic motion. They encode a lot. Actually, they encode much more information about the orbits, but here we just use it to illustrate how it allows to distinguish between regular and chaotic. So from the upper left corner to the bottom right, we increase the energy. First, three couples of plots correspond to regular off-equatorial motion. Then the cross-equatorial motion becomes possible, and the chaos sets on. in these recurrence plots, the regular dynamics appears as a simple diagonal patterns, but in the case of chaos, the diagonal lines become shorter, they break, and such complex structures may appear. What's the advantage of this tool? Is that its construction is simple regardless of the dimension of the phase space, unlike, for example, Poincare surfaces of section. But here we are still in the Waltz field where there are 2 degrees of freedom, so we can also use the Poincare surfaces to clearly distinguish between regular and chaotic motion. Review on this recurrence analysis may be found here in Marwan 2006. It shows more clearly the distinction between regular and chaotic dynamics as reflected by these recurrence plots. Well, and also these recurrence plots may be quantified easily. We may make some statistical analysis of these plots, and this is just to illustrate that how they can capture the change of the dynamic regime. Here we increase the energy of the particle. We see that the behavior of this parameter of this L, which is actually the average length of the diagonal line in the recurrence plot, changes dramatically at one place, and the other measure, which is the inverse of the longest diagonal line in the recurrence plot, also changes at the very same point, which is the energy of 1.685. And this we interpret as a place where the transition to chaos occurs. So this was just to demonstrate this rather novel tool for the given tasks. Here we switch to the equatorial lobe, by which we mean the situation where we have only the equatorial potential minima in the equatorial plane, the minima of the potential, and therefore, which also this topology, of course, appears also in Kerr-Newman spacetime, and it shows again that for some range of energies, the dynamics is mostly regular in these equatorial lobes, but if we reach above this, which is usually quite long range of energies, for which the regular dynamics dominates in the phase space. But once we increase the energy further, also the chaos will set on, and if we increase it even further, it will dominate the motion again. But compared to the situation in the cross-equatorial lobes, where the dynamics was mostly chaotic, here we have a long range of energies for which we mostly detect regular motion. Well, now finally we incline the field to describe or to analyze the general scenario of inclined fields. And this illustration shows the comparison of the originally regular orbit of equatorial orbit in the field with no inclination. So the red orbit is orbiting in the aligned field parallel with the rotation axis of the black hole. But when we incline the field, the same particle, all other parameters are fixed. In this case, becomes cross-equatorial and also becomes chaotic, which we find from the analysis of the maximal Lyapunov exponent in the right panel. In this plot, we actually compare several trajectories which only differ in the inclination angle of the asymptotical magnetic field, and there is a logarithmic scale on both axes, this is the integration time, and here is the largest Lyapunov exponent chi. And how do we read these plots? The regular trajectory would appear as a linearly decreasing line in this plot, like this green one. And because in the case of regular motion, the largest Lyapunov exponent is asymptotically 0 or asymptotically tends to 0. However, the chaotic, it's gone or gone. Last two slides. Or
you can continue.
Yeah.
But fast.
Yeah, it's almost. Yes. So what we see is that for a very tiny inclination of 0.0025, it's the tangent of the inclination angle actually. The orbit is still regular, so it opposes the perturbation by the inclining the field. But when we increase slightly the inclination, the plot of this leaves the trend of linear decrease, and it converges to some positive value, which is a hallmark of chaos, that the largest Lyapunov exponent requires a positive value. And we see that it's nicely stratified, that if we increase gradually the inclination, that also the value of largest Lyapunov exponent arises, which can be interpreted as in such a way that the motion becomes more and more chaotic in some sense, as measured by the Lyapunov exponent. And we also see that once we reach the inclination of 0.01 or something in this about this value, that the chaos is somehow saturated, that the value of this chi, of this large Lyapunov exponent, doesn't further rise. Well, this is the other situation when we depart from the originally cross-equatorial chaotic trajectory in the Waltz field. So this trajectory was already chaotic in the parallel field, and here we see that the inclination of the field doesn't change the dynamics significantly. Of course, the trajectory itself traces the inclination of the field, but from the point of view of this chi parameter of this Lyapunov exponents, this situation doesn't change much, which we interpret in such a way that once the trajectory is fully chaotic, for which we have the operational criterion that the Lyapunov time is roughly comparable to the azimuthal period of the orbit, but it's no general criterion. It's just apply this terminology here. That then, if it's already fully chaotic, that the chaos doesn't further increase by adding this extra perturbation by inclining the field. And the last figure shows the originally regular orbit in equatorial plane, which is the red one here, which is also shows the symmetry of the field because it's parallel to the rotation axis. But once we incline the field, also the whole trajectory somehow inclines, and its Lyapunov exponent also shows the transition to chaos. Here in this for this example, even the tiniest value of inclination led to the non-zero Lyapunov exponent. So in this case, the dynamics didn't oppose the extra perturbation by the inclination at all. So and then it also underwent the continuous transition to so-called full chaos as we increased the inclination of the field. So here is already my summary. In the first part, I conclude the situation in the aligned scenario, for which we observed that the off-equatorial motion is mostly regular, which is somehow surprising, because actually, even to allow these off-equatorial orbits, we need to have this non-integral perturbation, the magnetic field, which represents the non-integral perturbation, strong enough to balance the vertical component of the gravitational force, but still the dynamics is regular in this case. We observe the continuous transition from the regular to chaotic motion by increasing the energy of the particle. We saw that in cross-equatorial lobes the dynamics is mostly chaotic, and we also saw that dynamics in equatorial lobes is predominantly regular for some reasonably long range of energies, but then it also shifts to chaos. And the last part of the summary regarding the inclined magnetic field, we saw that the regular orbits are generally very sensitive to the perfect alignment of the field, and that the very low inclinations of, let's say, 1%, which is around 30 minutes, like a half of a degree, is typically sufficient to perturb the regular dynamics and introduce chaos. And we also saw that once the trajectory was originally chaotic in the aligned scenario, that the extra perturbation by inclining the magnetic field didn't change the situation much. That once there is a full chaos, that it's not anyhow increased by the extra perturbation. So the conclusion is that within given model, the stability of regular motion, or the regularity of the motion of charged particles, depends critically on the perfect alignment of large-scale magnetic field with the rotation axis of the black hole. And once the field was slightly inclined and the axial symmetry broke, then the chaotic regime started to dominate the dynamics completely. Okay, so thank you for